Okay, so I'd like to start by thanking the organizers. I know it's a lot of work to put together a nice program like this, and I think I like to speak late in conferences, but one of the disadvantages of being a late speaker in a conference like this is everyone's already said lots of completely true and very nice things about Menachem, so I endorse everything that's been said. I'm James Cummings, and I endorse this message, but so I'd just like to add a couple of things. So I owe great debts, personal and mathematical, to Menachem, and in particular, I look back and my years as Menachem's postdoc in Jerusalem in a long time ago now, in the middle of the 1990s, just really did change my life. And in particular, I got to know Matt, and me and Matt and Menachem pursued. So actually, they're still some of my favorites among my theorems. So, of course, we were all younger and more beautiful, as Matt reminded us. And I was kind of sad that I remember we failed a lot, but apparently our failures were insufficiently epic to make it into Matt's talk. But so something that I think maybe no one really said is there's this fantastic community around set theory and logic more generally in Jerusalem. And something about Menachem that everyone who's worked with him mathematically knows is that he has this gift for making complicated things seem very simple. And it's true with the community too, that kind of maintaining a thriving community like the Jerusalem set theory community, Menachem makes it look easy. If you try to do it yourself, you realize it's not easy at all. So I think we all owe him a great debt for that. So, okay, on to the mathematics. So I'm going to talk about, again, subjects close to my heart. And I think, Menachem's taste has informed my taste. So some subjects quite close to Menachem's heart, to various properties of trees. So I'm going to start with a question. I'm going to hopefully answer a question that was raised on the internet, actually, by Monroe Askew. So what Monroe observed is that in what you'd think of as the standard models where Aleph-2 has the tree property, there are no Aleph-1 Curepa trees. And he was wondering whether this is kind of a universal phenomenon. So the question is, does the tree property Aleph-2 imply there are no Curepa trees? Aleph-1. When I say Curepa, when I say Curepa tree without qualification. So an Aleph-1 Curepa tree, just to remind you, the tree property Aleph-2 says every Aleph-2 tree has a branch. A Curepa tree is an Aleph-1 tree with Aleph-2 branches. So let's just see what let's just look into it a bit and see what makes you think that this might be a reasonable question to even ask. So the two standard models that I think probably everyone would have in mind where the tree property holds at Aleph-2 are probably models of PFA and Mitchell's model. Okay, so let's just look into it a bit and see, why does PFA, so this isn't really the heart of the talk, but why does PFA imply there are no Aleph-2 trees, no Aleph-2 Einstein trees? Why does PFA imply there are no Aleph-1 Curepa trees? So, if one implies no Aleph-2 Einstein trees. So I think this was observed by Jim Baumgartner and was the earliest evidence that PFA would really have substantial large cardinal strength. And the argument goes something like this. So you start off with your putative Aleph-2 Einstein tree T, and then as usual with PFA, you want to cook up some proper forcing which does something. So the first thing we're going to do, I suppose, is we're going to force, or think about forcing. This is a PFA argument. But we're going to think about what happens if you really, truly force over V with the Levy collapse, col LF1, LF2. And, well, something bad has happened, but it's not too bad. The tree has kind of collapsed because LF2 has collapsed. So now if you take a cofinal set of levels of order type LF1, you can kind of crunch the tree down to a tree of height LF1. Okay, it looks rather broad. No, it looks rather broad because you have levels of size LF1. But the key point is PFA implies the continuum is greater than LF1. And that means that this countably closed forcing is not going to add any branches through this LF2 tree. So standard arguments, which I'm certainly not going to write down, but you say, suppose that you had, in this collapse forcing, suppose you had a name for a new branch, then you can build a perfect binary tree of conditions and corresponding partial information about the ways that this new branch is going. And after just many steps, you forced the branch. There's some level on which you forced so much splitting. The branch is, you've got 2 to the omega, which is greater than omega-1. It's omega-2, different ways. The forcing's countably closed, so you can take lower bounds for every branch through your tree of conditions. Okay, so the point is, what you have here, we have a tree of height LF1, no cofinal branch. Okay. And now, and again, another theorem by Baumgartner. If you have a tree of height LF1 with no cofinal branch, so you can do CCC specializing forcing, and you can make it into a special tree. Okay, so that's the situation if you actually do this forcing over V, that you end up with a tree which in a strong sense has no branch. So you've kind of sealed the branchlessness of your original tree. Okay, now the end game is just the usual thing. You just take PFA and you build a suitable pseudo-generic, and you end up with an initial segment of the tree T, which can't have any branches, which is kind of embarrassing because it's an initial segment and the tree continues. Okay, so and there's a kind of strong similarity with that proof and the proof that PFA implies no LF1 Kurepa tree. So this time, okay, there is only one picture in set theory, so here's the tree. Of course, this is a Kurepa tree now. So now before, the tree was quite tall and had no branches. In this picture, the tree is much shorter, but supposedly it has many branches. That's what makes it a Kurepa tree. So now this time, I suppose, covering my back, let's make sure that we do enough Levy collapsing to actually collapse the set of branches. Okay, well, once again, this time it's an LF1 tree, so really cardinal arithmetic isn't so important here. It's an LF1 tree, and therefore this collapse isn't going to add any new branches through this LF1 tree. And after we're done, what we've got is a tree which only has LF1 many branches. And now an LF1 tree with LF1 branches. So now another chapter of Baumgartner's work, I think it's Baumgartner, on specialization. If you have a tree with few branches, you can do something very like the specializing forcing for a branchless tree. And now you can do CCC forcing to freeze the branches in the sense that, well, you have to bite the bullet and admit that you've got some branches, but you can at least make sure that there will not be any more branches in cardinal preserving extensions. Okay, so now here what we have is T, I don't want to write it really. So T is an Aleph-1 tree, it's got Aleph-1 branches, and there's no way you're going to find any more. So now once again, and I'm glossing all details, you appeal to PFA and you say, actually, you know, the pseudo-generic that you build with PFA selects Aleph-1 many branches. Those are all the branches you'll have. Okay, so what I'm going to do is I'm going to at least sketch proof of a theorem. Thanks. Menachem's always giving me a hard time about killing flies with bazookas, and this is probably another case of killing a fly with a bazooka. So I'm going to say, there exists kappa measurable. Probably weak compact is enough. Didn't really think about it. Implies Aleph2 has the tree property, and there exists an Aleph1 crypt tree. So I'm going to use Mitchell forcing for this, and my excuse, one of my many excuses for not saying very much about Mitchell forcing is that the topic's already been quite extensively covered in Dima's very nice talks. So I'm just going to say, I'm assuming, remember, the kappa's measurable. So Mitchell forcing, we're going to be given a large cardinal kappa. So let's call it M. So Mitchell forcing, so in the Mitchell extension, we're going to have 2 to the omega is kappa, is omega-2, omega-1 is preserved, and kappa, which is omega-2, has the tree property. Okay, but as we'll see, and I think this is part of what Monroe observed, if you look in the Mitchell model, you are going to find that in the Mitchell model there are no Curepa and the reason, you can see there's a lot of similarity between this argument and this argument. And we're going to see when we look in the Mitchell model, the reason that there are going to be no Curepa on Aleph1 is going to be really very much the same as the reason that there are no Aleph2 Arenstein trees. So let's say the reason that I want to use a measurable cardinal is I want there to be, in the Mitchell extension, an actual generic elementary embedding with critical point omega-2 whose domain is the whole of the universe, just to save some time. So we can say, these are rhetorical questions. Probably everyone in the audience knows the answer, but so let's say, why does kappa, which is omega-2, have the tree property in this model? Actually, quite interestingly, this is related to some stuff I've been doing with various people, Menachem, Dima, Cy Friedman, Asaf Renat. You can actually kind of adduce 2 rather separate reasons why omega-2 has the tree property in this model. So I'm going to use the reason that I kind of understand better and learn first, which I learned from a paper by Uri Avraham about the tree property on Aleph2 and Aleph3, also mentioned in Dima's talk. So we can look at things this way. We can say N, B, M. Okay. We can force a generic elementary embedding with critical point LF2. So it's the usual thing. There's going to be a further extension. There's going to be a further extension, VGH, and in VGH, you're going to have J from VGM to some n, but n is going to be contained in VGH. Okay, so as usual, again, a very familiar picture to many people in this room. Okay, there is only one picture in set theory. Here's the tree T. It's got height omega-2. We stretch it with the generic elementary embedding. So what this buys us, we look on level kappa in J of T, and we say, look, here's a branch. That seems good. But the problem, of course, is that the branch a priori might not live in VGM. It might have been added by the same forcing that added the generic embedding. This is exactly the question that came up in Dima's talk a lot of the branch lemmas. We need some understanding of when the quotient forcing here is going to add a branch. So I think in Bill's original argument, there's a subtle argument involving fresh subsets. This thing here, this new branch, it's morally speaking a subset of the old omega-2. It's clearly novel if T was an Ahrenstein tree, but all of its small subsets, or all of its small initial parts, are old. Okay, but you can argue, and this is what I learned from Uri's paper, you can argue by a different route that you have you must have a branch actually in VGM. And the reason is, a priori, if you think about the natural forcing to add the generic embedding, well, Mitchell forcing is kappa CC, kappa's omega-2, so you expect to be able to lift this J with critical point kappa. So the natural forcing to add the elementary embedding is just force to complete the generic, just force, in the obvious way. Okay, this actually, it's okay forcing, but it's not super nice forcing. And the very nice trick that I learned from Uri's paper is you can actually write this forcing as in VGM. You can write this as the projection of a product of adding some number of Cohen sets and doing some countably closed term forcing. Okay, and now you have to start playing around, but I guess I'll say what's going on. So remember, in VG, 2 to the omega is kappa is omega-2, and now that I've got this nice projection argument, this forcing adds a generic embedding, so for sure this forcing is bigger, adds the same generic embedding. I want to argue that a product of Cohen forcing and countably closed forcing can't add branches. Well, let's think of it as an iteration. The definition of Cohen forcing is very absolute. Let's do the countably closed bit, followed by the Cohen bit. As before, this came up in the PFA argument, the countably closed bit, whatever it is, doesn't matter, certainly can't add a branch. However, remember, the countably closed bit, it's bigger than this forcing. This forcing was made from M by stretching it. M collapses kappa to LF1. So this thing here is going to collapse. Sorry, I misspoke. M makes everything less than kappa have size LF1. So J of M is going to make everything less than J of kappa have size LF1. So here it's very reminiscent of the PFA thing. Whatever this countably closed forcing is, guaranteed it's going to collapse kappa. So once again, we've got this picture of the tree being squashed to some tree of height LF1, morally speaking. But then the point is, Cohen forcing has as nice a kind of chain condition as you can wish. So in particular, Cohen forcing has the LF1 Nasta property. So it's got much more, obviously, but it's got the LF1 Nasta property, which says among any sequence of Aleph-1 conditions, you're going to find a subsequence of Aleph-1 many pairwise compatible conditions. Such a forcing, just easy argument, can't add a new branch through a tree of height Aleph-1. So this is the branch lemma, if you like. The key point is that the Cohen forcing is Aleph-1 Nasta after doing this bit. Okay. And now, I think probably at this point, you won't be very surprised when I kind of tell you why there are no Aleph-1 Curepa in the Mitchell model. Again, it's got a, in the same way that this kind of ran parallel to this, the argument that there are no Curepa in Mitchell's model is going to run rather parallel to the PFA argument. Okay, so, but let's do it. So why, I'm asking rhetorical questions now apparently. So why are there no Aleph-1 K-trees in the Mitchell model? Okay, well, so what I like about this, there's some kind of duality here between, here's another instance of the picture. It's called, the tree's always called T. Okay, this time, this is supposedly a Aleph-1 tree with at least Aleph-2 many branches. Okay, let's imagine making a list of them. So now the point's going to be, oh, I'm going to hit it with J. Actually, this time, J has critical point Aleph-2. This is an Aleph-1 tree, so J of T is T. But the set of branches this time is rather large. It's not that the tree is stretched, but the set of branches is stretched. So this generic elementary embedding that I was talking about over here is going to have to give us a new branch. Okay, so this time N, J, H, new branch. But now we're in exactly the same kind of difficulties that we were in with the tree property Aleph-2, that this business here, think of it as an iteration, countably closed followed by Cohen, has no business adding new branches to this Aleph-1 tree because the countably closed bit can't do it, and then the Aleph-1 Nasta Cohen bit can't do it either. Okay, so I think this is what makes Monroe's question so reasonable and also gives some kind of clue about maybe how we should think about this. So somehow, Cohen forcing is too nice, right? That was the problem. What we want is something that we want to think about force. Well, you know, we might want to think about the following kind of forcing: forcings that are Aleph-2 Nasta but not Aleph-1 Nasta. That's a kind of natural thing to think about. Okay, so you think about this, and you say, well, look, let's have a stab. Okay, let's make a instructive full start. Let's just do Mitchell forcing, and then let's add a Curepa tree. You know, we're optimists, right? You know, I always think Menachem is very optimistic, so we should be optimistic. So let's do Mitchell forcing, and then do standard forcing to add a Curepa tree. Of course, it's a disaster because when we did the Mitchell forcing, the continuum was blown up to omega-2, and of course, the standard way of adding a Curepa tree is going to be countably closed. So that crashes and burns. But here's where we can take a lot of inspiration from what Uri Abraham did in the paper with the tree property on Aleph-2 and Aleph-3, though that's actually a much more complex situation, but you have a similar problem. So in Uri's setup, so Abraham, you're getting the tree property on both Aleph-2 and Aleph-3. So here, you're going to start off with two large cardinals, kappa and lambda, and you're going to do a kind of iterated Mitchell forcing, where in the first round, this thing here is going to become 2 to the omegas, omega-2 kappa. Okay, now you want to do another round of Mitchell forcing. So naturally, what you want to do at the second round is you want 2 to the omega-1 is omega-3 is lambda. Well, if you want this by itself, over a model of GCH, I mean, Mitchell forcing is very generalizable. It works very nicely to make the double successor of your favorite regular cardinal have the tree property. So if you just wanted this, you'd be fine. But you don't want this to destroy this. So you really have to do this forcing over something like Mitchell forcing over this model. You want to blow up the power set of omega-1 to omega-3 with some nice forcing, but you're in the situation where 2 to the omega is omega-2. So the trick, I mean, there's a lot more going on in Uri's paper. He's really doing something very hard there, but the trick, which is kind of going to give us inspiration, is the second round of Mitchell forcing is going to be defined in this paper using Cohen conditions from the ground model. So here's the idea here. We're going to blow up the power set of Aleph-1 to lambda using add omega-1 lambda in the sense of V. Well, okay, at first blush, maybe it's not obvious that this is a good idea, but it turns out the easiest way to see this is to use that same kind of product analysis that I mentioned before. The Mitchell forcing itself can be read as the projection of a product of some Cohen sets and some mysterious, countably closed term forcing. If you look at things in that light and make a lot of uses of Easton's lemma and such, you can see this is actually still pretty decent forcing in this model. Okay, so that's kind of that's the trick. So I think I'm going to suppress as many technical details as I possibly can, and I'm going to try and just give the main thread. So the idea, the result. So start with kappa measurable. Then there are going to be two rounds of forcing. One, do Mitchell, just vanilla Mitchell. Another very interesting thing that happens in Uri's paper is he showed us how to do Mitchell forcing with look-ahead so that you can kind of insulate the tree property against bad generic stuff that's going to happen later in the construction. But here we can actually get away, because we're only doing one round really, we can actually add one tree, have two branches, just using a countably closed forcing. So I'm going to call Mitchell M for Mitchell, countably closed forcing, K for Kurapa. Okay. So okay, so that's it, but I guess maybe I should say a little bit about why this works. Right. Let's see, okay, good. Arthur, did I start on time? I think I did, right?
5 minutes.
Hmm?
You have 5 minutes over.
Oh, okay. I think I don't need it, actually. Okay. So, well, let's see what's going on. Okay. So, once again, we like generic embeddings. I mean, if Menachem's formed my taste, this is one thing. In fact, I remember when we were postdocs in Jerusalem, I think Mirna actually threatens to bludgeon me if I said one more time, the right way to think about this is through some generic elementary embedding. So, but I'm going to say it anyway, the right way to think about this is through some generic elementary embedding. Well, and once again, life is cheap and easy, as it sometimes is, because, you know, we're living in the land of things that have nice, robust chain conditions. So, you know, this is just product forcing, right? Because I did Mitchell, but then I added my tree using conditions in the ground one. Just product forcing. And I think both the factors actually have very robust chain conditions. So the product has very robust chain condition. So we're just going to end up, we're going to lift J, my initial, you know, something witnessing that my initial kappa was measurable, to J, which is going to go from VGH, but it's really G cross H. It's going to go to M J of J, J of H, which is just J of J cross J of H. Okay. So compared to some situations that you have to think about, this really isn't too bad, right? You can understand very clearly what did you have to do to get from this model to this model. Well, you kind of had independently, mutually generically, you had to complete G to some J of G by some mystery forcing JG over, you know, JM over G. You had to complete H to J of H by some forcing J of K over H. All right. So now, you know, this, I've got this tree T. As usual, you know, if I wasn't shooting flies with a bazooka, I would probably have reflected this whole story to some alpha below kappa on the V side. But I'm shooting flies, so I'm going to just say, look, okay. Okay, so now it's I think many members of the audience are going to appreciate. It's going to be, once again, exactly the situation of a branch lemma. I should say what I'm doing. Okay, let me stop and say what I'm doing. I'm trying to make a model where LF2 has the tree property and there's an LF1 Curefa tree. But I took care of the LF1 Curefa tree bit. So really, my business is to verify the tree property. So once again, I've got a tree T. Once again, I stretch it. Once again, I have a branch. Once again, my problem is to see that I have a branch inside this submodel. Okay, so now, and again, I wrote a paper with Matt. It was, I don't think it was an epic failure. I think it was quite an epic success, actually. So I read a paper with Matt that Dima was mentioning where we showed that consistently LFN can simultaneously have the tree property for finite n greater than or equals 2. And that's kind of a messy argument to make, because there you have infinitely many supercompacts, and you collapse them hand over hand by some iteration of Uri's methods in this paper. But there it's a big mess, because you have a generic embedding. It's added by some rather complicated forcing. You look at the branch that's naturally added by the generic embedding. It shows up in some extension, which is actually a little way from the place where the tree lives. And then you have to find the right path through some kind of maze of intermediate generic extensions, seeing that at each point you've got some suitable branch lemma to get you through. So, yeah. This one isn't so bad, actually. Okay. Let me just point out one thing. So this is maybe the one slightly finicky point. What is J of k over h doing for us? Okay. Well, J of k over h is taking the generic curepertree, which was already added by h, the generic for k, and it's blowing up its set of branches. Okay, so it's taking this Aleph1 tree, which I think has Aleph2 branches in the place where it initially lives, and then it's blowing up its set of branches. So for certain sure, this is not an Aleph1 Naster forcing. But you can arrange things, it's not very hard, so that actually J, K over H is actually Aleph2 Naster in VH. Okay, so if you're used to the tree property arguments, you have to kind of adjust your thinking a little bit here, because we're very used to this picture of how the generic embedding lives in some forcing which collapses the height of the tree. But here, there are two aspects to this. There's the kind of vertical aspect where you're stretching, and then there's the other aspects where you're blowing up. So, in particular, there's another tree floating around here, which I didn't even bother to give a name to. Call it U, the generic curepertree. So the job of this quotient forcing is to blow up the set of branches of U. Okay. All right. So now we want to find the right path, the true path, from the model MGH up to the model MJGJH, making sure that we didn't mess up adding branches at each stage. So it turns out, I'm keeping an eye on the clock, it turns out that the correct order of events in this argument, or at least the one that seemed easiest to make work, was to do this. Okay, so what's the point? So how do we distribute so? Okay, so the quotient forcing is countably distributive and Aleph2 Naster. Right? And that's good news because, in particular, by virtue, remember, we haven't actually collapsed the tree at this point. You know, we've actually done some. We haven't actually, T is still looking like an Aleph2 tree at this stage of the game. It's what happened down much lower. The generic curepertree had its branch set blown up, but that's a detail. Okay, so now what we want to do is we want to see that the step where we do a tail of Mitchell forcing doesn't mess us up. We want to see that doing J of Mitchell over G doesn't mess us up. But actually, you know, this is not too bad because the product analysis of Mitchell forcing is actually pretty robust. That in MG, you've got this tail forcing. J of MG is a projection of Cohen times countably closed. That's what makes everything go, right? That's why we are in good shape with not adding branches. And that's why I just like that, that's why I like it that this bit here is countably distributive, because I just did a countably distributive extension. So this product of an analysis of Jm over G that you can do in MG, it still actually, maybe it's even easier than I'm making it look. It still actually makes perfect sense in the model MGJH. The rest of the forcing that I need to do to complete the generic still looks like a product of something that's Cohen and something that's countably closed. So now, as usual, so this bit here means no new branches, which is good. And this bit here means no new branches. Okay, so, all right, I think no one ever lost friends by finishing a bit early, so I'm going to finish a bit early, and so there it is. And
Are there any questions?
yeah, Mena.
Yeah, so then how about putting this concept to
Yeah, I thought about that. If anyone cares, I don't think it's that bad, actually, because, for example, if you look at the paper I wrote with Matt, we were at pains to make a rather modular story where you have some abstract version of ritual forcing where you feed in certain data and you just have to verify that the posets you're feeding into this kind of meta construction have certain properties. So I do not see why you would have any trouble if you cared to doing this from all cardinals. I don't see that there'd be any obvious problem. If anyone wants it, you can do. Out of 2 and out of 3, I think that tree property, there are out of 1 and out of 2 Currier trees. Also, if anyone wants a out of 1 tree with more branches, that's very easy too. In fact, really, the forcing about a Currier tree is very boring, and pretty much all branches are the same. So if you take a tree, if you took a tree that lived in an extension where you've done Mitchell and then added a tree with a ton of branches, that tree would just live in a sub-extension which looks like this. So you can have, if you want, more branches. It's not very surprising because this was all inspired by what's going on in Uri's model. And in Uri's model, for other reasons, he actually wants the tree property, but in Uri's model, you actually have 2 out of 1s out of 3. The big problem with all this stuff, by the way, is that you have power sets overlapping the critical points of your generic elementary embedding. So, in Uri's model, and also my model with Matt, an instance of the kind of troubles that you have is you have 2 to the omega-1 is omega-3 in a model where you're very concerned with generic embeddings with critical points omega-2. So, and you also want the power set of omega-2 to be omega-4. So all kinds of stuff gets stretched by the generic